Hello everyone and welcome back. Today we're going to continue our discussion on fluid dynamics and more specifically for Bernoullis equation. In a previous video we saw how a fluid always accelerates towards lower pressure regions. So in other words, it always goes from high pressure to low pressure. And according to pressure depth relationship, imagine now we have a tube that changes in height, just like you see in diagram B. So if we look at the two regions, always the lower region is going to be higher in pressure and the upper region is always going to be lower in pressure, provided that the area of the pipe does not change. What if it now does, as we see in the diagram A? So what do we have now? Now we have a change in both the diameter, which according to the continuity equation is going to increase velocity, and also now we have a change in height. So let's derive Bernoullis equation and let's see where this came from. So when we're talking about Bernoullis equation, the only thing really it is the law of conservation of energy. That's all it basically is. So if we're looking at the law of conservation of energy, at the heart of it, we see that we have to look at the total amount of work that is occurring in that pipe as it's changing diameter and at height. So work, as you recall correctly, it is really force times time. That's all it basically is. So previously, when we did fluid statics, you saw that force is something very, very specific. It is pressure times area. That's what basically force is. So it's pressure times area times time. And more specifically now, pressure really is going to be the change of pressure, because that's what is going to determine really the amount of work being done, times area times time. And if you further recall, area in time, that leads to really volume. That's what volume basically is. So notice how our work equation, we went from work to change of pressure times volume. And everybody knows change of pressure. That, of course, is going to be pressure 2 minus pressure 1 times volume. So that's what work is. Now let's look at the work being done on the particles. So the work now is going to be what? It's going to be a combination of two things now, because particles are obviously moving with a certain velocity. They're going to have kinetic energy, and also they're going to be changing height. Therefore, they're going to have potential energy. So if we look at now the change of work from point of view now of the particles and not of pressure, we clearly going to see that it is going to be the kinetic energy, which is 1/2 times mv squared of position 1 plus the potential energy of position 1, which is mgh1, subtracted now from the kinetic energy 1/2 mv2 squared from the second part, minus the potential energy from the second part, mgh2. So now we can actually make these two equations equal with respect to each other. So what does it become? It becomes now pressure 2 minus pressure 1, because that's what work is, as we said right over here, times volume, equals now 1/2 mv1 squared plus mgh1, that's all in parentheses, minus 1/2 mv2 squared minus mgh2. So we just simply took the two work equations, we made them equal to each other. So one thing we can do is we can get rid of now the volume. So we take every term and we divide it now by volume. And when I'm talking about every term, I mean every single term. So we multiply kinetic energy first, we divide it by volume, potential energy first, we divide it by volume, kinetic energy second, divided by volume, and potential energy second, divided by volume. So what is the consequence of this? Volumes on this side are simply canceled out. So we're left with P2 minus P1 equals now the kinetic energy is going to be what? 1/2. What is mass divided by volume? Simply density times velocity initial squared plus mass divided by volume again, density times g times height 1, all that of course is in parentheses, minus, okay, 1/2 density times V2 squared minus now again M over V density times G times H2. So from this, we can simply separate the two terms. We can take this term, bring it on this side. We can take this term, bring it on this side. So what do we basically have? So we have P2 now. We bring this entire term right here. So it becomes minus 1/2 rho V2 squared. So it's going to be minus is going to now become positive. And this over here is going to be positive as well because we're bringing it on this side. And it becomes rho GH2 equals now, we take pressure 1, we bring it on this side, so pressure 1 plus 1/2 rho V1 squared plus rho GH1, as you can see right over here. So this is our Bernoullis equation, as you guys can see right here, and this is what we're going to use for every single problem now in order to solve the various problems that we have to come up with. So as we just said, it's really the relationship between the pressures as well as the kinetic and potential energies at each point. So going back to our presentation, we can see that this is of course the derivation, as you can see right here, and we move down. So this is of course Bernoullis equation, and of course it states that in a steady flow of non-viscous incompressible fluid, the pressure, fluid speed, and elevation at 2 points are related by the following equation that we just described, and I just showed you how to derive. So now, this has some very, very, very important effects. So for example, we can explain why there are certain physical principles that are occurring in everyday life, such as a truck that is stationary and a truck moving with a constant speed. We can actually see that the tarp will actually bulge upward, as well as how Bernoullis principle keeps an airplane in the air. So how can we use Bernoullis equation in order to account for both of these behaviors? It's actually very, very simple. So we go back to our sketch pad, as you can see right here, and let's look at this equation. Okay, so imagine now we're talking about the truck, okay, that's stationary. So if we look at this equation, okay, what can we basically see? A truck that's stationary, for example, obviously, even when it's moving, is not going to have absolutely any change in height whatsoever. So we can cancel these two terms out. And also when it's stationary, so we're going to take that as part 2, we can simply cancel this out. So what are we left here with here? So this equation now becomes pressure 2 equals pressure 1 when it's basically moving plus 1/2 rho V1 squared. So look at this equation very carefully. So what does this mean? This means that when we have a steady flow of particles with a certain velocity, so as basically velocity goes up, in order to keep this equal to pressure 2, what's going to happen? Pressure is going to drop. And that's at the core of Bernoullis principle. When the flow of particles increases in velocity, the pressure will go down. So let's go back and explain our different scenario in the presentation. So when the truck is moving, the flow of air over the tarp is actually going to cause a decrease in pressure, and there's going to be more pressure inside the trailer, so it is going to push it outward and it's going to bulge it outward. The same thing with the airplane. As you can see right here, up atop of the wing, because it's curved, we're going to have faster air. Because now we have faster air, we have lower pressure, we have slower air, higher pressure at the bottom. It is going to create a lift force, and that's what creates a lift in order for airplanes to basically fly throughout the sky. So at the basic once again, at the basic core of Bernoullis' principle, as the velocity of particles increases, the pressure is going to decrease. Thank you very much. See you soon.